Hello everyone, I'm pleasant to attend the HotStorage workshop this year. My name is Shukai from the Institute of Computing Technology, Chinese the maker of sense. The title of my paper report today is splitting I/O paths for different sized key value items without linear storage device. In this report, I will first introduce the background and the motivation of our work. Then, I will present the design choice for splitting I/O paths as well as the evaluated results. Finally, I will conclude our work and present a fair discussion issue. So first is the background. Key value store are divided deployed as a key component of storage infrastructure to today's data center. They usually serve interactive applications such as web searching, command, social network, such as present key value store, LevelDB, RocksDB, and in-memory key value store, such as Redis and memcached. Thus, key value store are required to provide fast data access to ensure service quality for up-level applications. The size of key value items are important workload factor for key value store. A few works have analyzed the real-world key value store workload and reported that the size of key value item vary from a couple of bytes to hundreds of kilobytes, such as Facebook's analysis on memcached workload found that more than 18% of requests are less than 500 bytes in size. On the other hand, the workload on a typical day in Baidu shows that over 19% of requests are greater than 118 kilobytes in size. Conventionally, storage devices are block-based, such as hard disks and solid-state drivers. Their random access is slower than sequential access. Over the past decade, a number of research efforts are made to design optimize block device-based key value store. Log struct merge tree is a typical example and is divided adopt existing key value store. LSM tree-based write date to a buffer in memory, then base date to SSD when the buffer is full. In this way, LSM tree-based key value store convert random write to sequential write. It achieves better throughput due to the better sequential access performance of conventional block device. However, LSM tree required to conduct data compaction to reclear KV pairs, which cause write amplification. This degrades key value store performance. Recently, advanced storage devices such as NVMe-based present memory and NVMe-based SSD exhibited different performance features compared to conventional block devices. This provides new design choice for building high-performance key value store. On the other hand, modern NVMe-based SSD such as Intel Optane SSD sustain high throughput with sub-millisecond latency. It provides similar performance for both sequential and random access. This motivates the research effort to bench KV requests and write to SSD direct without committing log and sorting on disk. For example, KVell adapts this design choice. On the other hand, no value memory-based present memory such as Intel DC present memory provides better addressable access and sub-microsecond latency for directly present data. Also, there are some works use low-tail latency features of present memory. They build a present buffer in RocksDB and LevelDB to reduce the logging overhead. In this work, we focus on the combination of both present memory and NVMe-based SSD. As shown in this table, present memory is friendly to serve smaller data, and meanwhile, this advantage is weakened when data size increases. For example, when data size is 64 bytes, the write latency of Optane SSD is 79 times that of present memory. When the size increases to 64 kilobytes, this value is reduced to 3. On the contrary, modern NVMe SSD suffer from read-write application when serving smaller data. Meanwhile, as we mentioned, the set range of real-world key-value workload are from a couple of bytes to hundreds of kilobytes. So in this paper, we mainly discussed how to build an effective key-value store by exploiting the performance feature of these advanced storage devices. Next, I will present the key idea of our paper as well as some design issues. Because present memory is most suitable for processing million atoms and NVMe-based SSD is suitable for handling larger granulate data. Thus, the key idea of our paper is simple. We let key value store adapt different I/O paths for smaller and larger key value atoms. We name the proposed key value store as SplitKV. This figure shows the system overview of SplitKV. I will first introduce its overview and then present the challenge. For smaller KVell atoms, SplitKV directly writes them to present memory. Meanwhile, for larger key value atoms, SplitKV bench write larger key value atoms to SSD without sorting them. Compared with the larger capacity SSD, present memory capacity is limited. Thus, when present memory capacity reaches saturation, SplitKV needs to reclaim present memory space. It selects part of key value atoms and migrates them to SSD. Unlike storing no-sorted large key value atoms in SSD, when we hand smaller key value atoms, they will be sorted and written to SSD to become a sorting table. This is beneficial to reduce the real read application and increase throughput when performing range query. Since the data in present memory and SSD are stored out of order in order to support effective query, we establish a present B plus tree in present memory to index global data in present memory and SSD at the same time. For the global present index B plus tree, we use existing research work FastFair. The key point of SplitKV is to split the I/O path of the writing data. At the same time, it also faces two challenges. First, because SplitKV need to decide whether it is writing to PMEM or SSD according to the size of key value store. Therefore, we need to consider that how to decide the size boundary of key value atoms. The second challenge is to handle the limited present memory space. Since the space of present memory is limited, key value atoms in present memory need to be migrated to SSD for reclaiming present memory space. Therefore, we need to consider that how to handle the merging of smaller items. Next, I will explain how SplitKV handles these two challenges. We separately evaluated the latencies of data accessing under different I/O paths. For I/O path 1, key value pair are written to present memory and then migrated to SSD through a background third. For I/O path 2, key value pair are directly read to SSD. The right table shows the average latencies when adapting different I/O paths for different size key value atoms. The ratios index the write latency benefit of writing key value pairs in present memory first and then migrating to SSD. As shown in table, the benefits start to decrease when a key value atom is equal to or greater than 4 kilobytes. This is because the background migration compacts for more present memory bundle-wise. For migrating larger key value items. This SplitKV sets the set boundary of a smaller key value pair to be 4 kilobytes. Any key value pair whose size is equal or greater than 4 kilobytes is considered to be larger one, and they will be directly read to SSD. The second challenge is to handle the limited present memory space. Since the space of present memory is limited, key value items in present memory need to be migrated to underlying SSD for reclaiming present memory space. As SplitKV applies a pending write to smaller key value item in SSD, any updates to an SSD smaller key value pair bring expensive garbage calculation. Thus, SplitKV adapts hotness of one key value migration and figure out key value items that are less frequently accessed for migration. In such doing, smaller KVell item writes to SSD are usually rarely accessed, which reduces the read-write amplification of SSD. In this paper, we apply a simple politic for demonstration purpose. We set a weight for each KVell item by using its access counts. SplitKV runs a background third to calculate the average weight of all key value items in present memory. When the present memory capacity usage goes beyond the 30 threshold, SplitKV selects the key value items whose weights are lower than the average one. These select key value items are then migrated to SSD. This figure shows an example. There exists 6 key value items with different weights in present memory, and the average weight is 3. SplitKV selects the key value items with the key of 1, 4, 5, and 6 as the code 1 as their weights are less than 3. These 4 key value items are flashed to SSD. The weights of key value items with key 2 and 3 are updated by being subtracted by 3. So now I will present the evaluation result for SplitKV. This is our experimental environment. We conduct all experiments on a server equipped with 16 4GB memory, 1 Intel Optane SSD, and 1 Intel Optane DC present memory. We compare SplitKV against RocksDB, KVell, and NoveLSM. We use the 6 default workloads in VSSB for evaluation. The description of each workload is shown in the table. We first warm up a 200GB database. All workloads include smaller key value items with 256 bytes value and larger key value items with 4 kilobytes value. Each workload has 126 GB data size, in which smaller, larger key value items account for half respectively. We first evaluate the latency of single key value store third. This table shows latency results of different key value store and zip-for-scale workload. For workload A and F, SplitKV reduced latency by several times compared to NoveLSM, RocksDB, and KVell and zip for workloads. LSM tree-based NoveLSM RocksDB perform compaction to insert ordered data and recycle invalid data. This causes high rate amplification and reduced performance. KVell applies in-place update for all key value items to avoid sorting overhead to achieve better performance. However, KVell suffers from read-write amplification for smaller key value items. Instead, SplitKV writes smaller key value items in present memory to accelerate key value accessing. Moreover, SplitKV exploits present memory to conduct in-place update for smaller key value items to reduce read-write amplification. Thus, SplitKV further outperforms KVell. For read intensive workload B, C, and D, SplitKV and KVell achieve better performance than NoveLSM and RocksDB due to the adapting of global B+ tree index. KVell doesn't sort smaller key value items in SSD. This introduces read amplification to KVell when serving scan query, by reading a lot of blocks. Thus, KVell suffers from the highest latency. NoveLSM and RocksDB performance better than KVell as they sort all key value items in SSD. SplitKV doesn't sort larger key value items in SSD, which reduces CPU overhead. Meanwhile, SplitKV flash sorted the smaller KVell item into SSD, which helps to accelerate scan performance. These two tables are compactions of latency and different workload scale. Note that the compared to the result under zip4 workloads, the latency improvement of SplitKV decrease under uniform workload. This is because the current hotness where migration policy is difficult to figure out code items under uniform workloads. Finally, we evaluated the throughput of SplitKV. The figure shows the throughput of different key value store with first-third and YSSV mixed workloads. You can see that the throughput of SplitKV is up to 3.5 times that of other key value store under uniform workload. The throughput of SplitKV is up to 7.9 times that of other key value store under zip4 workload. Finally, I would like to conclude our paper. First, modern NVMe SSD and present memory provide different access features when serving smaller, larger data. We propose SplitKV to provide different I/O paths for different size key value item for building key value store with such advanced storage devices. Our evaluation shows that SplitKV outperforms states of the other key value store in terms of both throughput and latency. This is conclude my report. Thank you for listening.